All right, today we're going to be building a seriously powerful physics toolkit. We're going to forge three absolutely essential tools: friction, this thing called a pseudoforce, and a solid method for tackling connected systems. Ready to get started? Let's jump right in. You know exactly what I'm talking about, right? The light turns green, the car guns it, and you feel like you're literally being pressed back into your seat. It feels so real, like some invisible force is pushing on you. But is there? What is actually going on there? We are going to solve that exact puzzle today. Okay, first up in our toolkit is a force that you and I deal with every single second of every day. It's the reason a coffee mug doesn't just slide off the table. Let's talk about the force that always fights back: friction. So at its core, friction is really just the resistance that one surface feels when it tries to move over another. And the key thing to remember is that it always, and I mean always, acts to oppose that motion. It's kind of like the universe's natural brake pedal. But here's the cool part. Friction isn't just one simple thing. When you're trying to push something that's not moving, you're fighting static friction. And it's smart. It actually adjusts its own strength to perfectly match your push, but only up to a certain point. Once you push hard enough and break that grip, kinetic friction takes over. And this one's a constant, weaker force. That's the exact reason why it's always harder to get that heavy box moving than it is to keep it sliding across the floor. All right, let's grab our next tool. Now, this one is a little bit of a mind bender, but it's super useful. We're going to go back and investigate that invisible push you feel when a car takes off. No, really, that force you feel, the one that seems so obviously there, it's not a fundamental force of nature like gravity or magnetism. Physicists actually call it a phantom or fictitious force. So what's going on then? Well, Newton's laws are perfect when you're, standing still or moving at a steady speed, but the moment you're inside something that's accelerating, like that car, things get a little weird from your point of view. It seems like there's a new force. So physicists came up with this really clever workaround. They invent a pseudoforce just to make the math work out in these accelerating situations. And you know what? The formula for this phantom force is incredibly simple. It's just the mass of the object inside the accelerating frame multiplied by the acceleration of the frame itself. And that little negative sign, that's the whole secret. It tells us the force always acts in the opposite direction of the frame's acceleration. So the car accelerates forward and you feel pushed backward. See? It all just clicks into place. Okay, now that we have our first two tools, friction and pseudoforces, let's actually put them to work. We're going to look at how to solve problems where you've got multiple objects that are all connected and moving together as one big system. This is a classic textbook setup you see all the time. You've got two blocks on a perfectly smooth surface tied together with a string. We pull on that first block with 16 newtons of force. So the big questions are, how fast does the whole setup accelerate, and what's the tension in that string connecting them? To crack this, we're going to use a really simple, repeatable three-step method. First, you just isolate each block and draw all the forces acting on it. That's your free body diagram. Second, you write out Newton's second law, F equals ma, for each block. And then third, you just solve those equations together to find what you're looking for. It's basically a foolproof blueprint. So let's find that acceleration for the whole system. It's actually way easier than you might think. We can just pretend the two blocks are one single object. So the total force is 16 newtons, and the total mass is 5 plus 3, so 8 kilograms. Force divided by mass, that gives us a nice clean 2 meters per second squared. And now, what about the tension? Well, for this, we just look at the second block, the 3 kilogram one. The only thing pulling it forward is the tension in the string. So we just multiply its mass, 3 kilos, by the acceleration we just found, which was 2. And that gives us a tension of 6 newtons. See? Simple, right? The method just works. All right, now let's really turn up the heat. We're going to see how this toolkit isn't just for simple problems, it's absolutely essential for cracking real-deal, high-stakes exam questions. Check this one out. It's from a past medical entrance exam. We've got a block on a wedge, but the wedge itself can slide around on a smooth surface. Okay, now that adds a whole new layer of complexity. How in the world do we even start with this? So the big trick here is realizing that everything is in motion. As that little block slides down the wedge, it's actually pushing the whole wedge backward. So you can't just analyze the block by itself. You have to treat both the block and the wedge as interconnected parts of one system. The movement of the wedge directly affects the block's path, and you have to account for that in your equations.
Let's try another one. This time we've got three masses, a pulley, and this is the important part, the two masses are on a rough horizontal table. That word rough is a giant clue. It's telling you that our first tool, friction, is definitely going to be part of the solution.
The easiest way to think about this problem is like a tug of war. The hanging mass is providing the pulling force, trying to get everything to move. And our friction tool helps us figure out the total force pulling back from the two blocks on the table. The net force is just the pulling force minus the friction. And once you have that, the acceleration is simply that net force divided by the total mass of all three blocks combined.
Okay, for our last example, let's look at a classic elevator problem. We've got a person inside a lift, and the whole thing is accelerating upwards. This problem is great because it brings together our ideas about forces and systems all in one place. The trick here is just to simplify. Instead of thinking about the person and the lift separately, just treat them as one single system with a total mass of 1,000 kilograms. The net upward force, which is the tension from the cable pulling up minus the total weight pulling down, is what causes that upward acceleration. If you just rearrange the formula, you find that the tension has to support both the weight and provide that extra kick for acceleration. So the tension ends up being the total mass times G plus A. Phew! So, after that pretty intense workout, let's take a step back and get our new toolkit nice and organized. Let's recap the essential tools we've put together today. So, here it is, your brand new toolkit, all in one place. For kinetic friction, just remember that force depends on the type of surfaces and how hard they're being pushed together. For the pseudo-force, think of it as a special tool you pull out whenever you're analyzing something from inside an accelerating system. And for all those connected bodies problems, the game plan is always the same. Apply F equals ma to each piece and then solve them all together. This right here is your cheat sheet for a massive range of physics problems. So, we've built the toolkit, and we've definitely seen it in action. But now the last question is really for you. The next time you're in a car that's speeding up, or riding in an elevator, or even just sliding a book across your desk, can you actually see these principles playing out? Where else do you see these forces, both real and phantom, shaping the world around you?